So for this experiment, we are going to rank the solutions based on their pH value. The experiment is two parts. The first part is your prediction. So this is what you predict for these 0.1 molar solutions. Which one is going to be the strongest acid? So you're going to rank them from the strongest acid to the weakest acid. And we know that the weaker the acid, the stronger is the base. So we're expecting here to be the strongest base. And then the second part is going to be the actual experiment where you are going to look at the pH values for the solutions that you predicted, and you would see how your prediction goes. So in order to start with the first part of the experiment, we do have to predict the acidity of several solutions. So what we know here is that as the Ka value of the solution increases, as the acidity increases. So what is a Ka? Ka simply indicates the extent to which an acid dissociates in the solution. Or the value of the Ka it simply is a direct representation of the acidity of the acid. And as the Ka value increases, as the acidity is going to increase. So we're expecting that strong acids are going to have a Ka, which is basically large. So a Ka large means that the Ka is greater than 1. And weak acids are going to have a Ka, which is small. This means that it is going to be less than 1. Now, there's a direct relationship between Ka and pKa, and the pKa is equal to minus log Ka. So if we have the Ka value, we can put it in this equation and get the Ka. So if we want to determine the relationship between pKa and acidity, as the pKa decreases, as the acidity is going to increase. So we're expecting now strong acids to have pKa's normally that are less or equal to -2. So if we're talking about, for example, -3, -4, -5, all of those are less than -2. So the smaller is the number, the higher is the acid. And we expect that strong acids are going to have low pKa. Weak acids on the other end, their pKa is going to be in between -2 and 12. Okay, so we as the pKa increases, you can see over here as the acidity is going to decrease, and we're expecting the solution to be more basic. And then we have the term dissociation, because we know that acids, whenever we put them in water, they simply dissociate in water. So what do I mean by this? Here I have an example of a strong acid. And a strong acid, whenever you want to dissolve it in water, it's going to dissociate completely. So we say this is 100% dissociation. So all the HCl are going to turn into ions in the solution. So you're going to end up having an H plus and the Cl minus aqueous in there. This is reflected by a Ka value that is very large. It's 1.3 times 10 to the 6. So we said that the Ka for strong acids is greater than 1. So this one is very large, and it indicates that the acid dissociates completely into H plus and Cl minus. So we say that this one is going to be 100% dissociation. And that is going to be your reasoning whenever you are working with these acids in there. So HCl is an example of a strong acid. Another strong acid is the sulfuric acid, and both of those are strong acids in there. So the reasoning is going to be these are strong acids because they do have a high Ka value and they are 100% dissociated in the solution. Sulfuric acid, on the other end, is another strong acid. And this acid, unlike HCl, has 2 hydrogens that can dissociate. Not just one, 2 hydrogens. This one has 1 hydrogen that can dissociate. And the dissociation is carried by 100% dissociation. This is why it's a strong acid. This one is the same thing. Its first step is 100% dissociation. This is why its Ka is very large. And the first hydrogen is going to dissociate. This is a diprotic acid into H plus and HSO4 minus. So the first dissociation for the first hydrogen there, it's going to be 100% dissociation, reflecting its high Ka. Now the second dissociation, this is still an acidic hydrogen. It's a conjugate base for the H2SO4, and it is an acid now in this equation. So the HSO4 will lose a hydrogen, but the dissociation here is not 100% dissociation, and this is why you see that the Ka value is less than 1, making that the conjugate base, which is now an acid, is a weak acid. So this one is considered to be a weak acid. So that is going to be an H plus SO4, and it is going to be a 2 minus, and that is going to be an aqueous. Both of those are aqueous. So if I want to compare the acidity between HCl and H2SO4, I would say HCl is a stronger acid. Reason why? Because HCl undergoes 100% dissociation, loses one hydrogen. On the other hand, H2SO4 is another strong acid, but it is not as strong as HCl because H2SO4 has two hydrogens to lose. It loses the first hydrogen by 100% dissociation. So the first step of the dissociation is 100%. This is reflected by the Ka value. The second step is going to be a weaker acid, and it's reflected by its lower Ka value there. So if I want to rank them, I would start with the HCl and then the H2SO4. The reasoning in here, as I said, for the HCl is 100% dissociation, Ka very large. Here it's a diprotic acid. So the first step is 100% dissociation, K very large, and then the second step it's going to be a weaker acid. Again, you are going to rank them from the strongest acid to the weakest acid. Okay, so these are the compounds that or the solutions. We do have a 0.1 solution of each, and we are ranking them based on their pH value. So we're going to talk about the pH in a second, but first let's go ahead and explain what weak acids are. So we explained what strong acids are. Gave two examples on strong acids. They undergo 100% dissociation. Weak acids. Now, weak acids, they do not undergo 100% dissociation, meaning that some of the acid is going to turn into ions, and the majority of it is going to remain as an aqueous in the solution. It's not going to dissociate. That is going to result with not 100% dissociation. So I would say that it is not 100% dissociation. This is a definition of a weak acid. So a weak acid by definition is an acid that does not dissociate completely, meaning that not all of its hydrogens turn into H plus. Some of them, they do remain in the solution. This is going to reflect by a low pKa or a low Ka, a low Ka value in there, okay? Because we said that weak acids, they do have a Ka which is less than 1. So once you see your Ka in the negative value, then you know that this is going to be a weak acid. An example of this is an acetic acid. Acetic acid is a weak acid. So we are given, as we mentioned, 0.1 molar solutions, different types of solutions. These solutions are either basic or acidic. So the first thing that we are going to do is we are going to arrange, put the acidic solutions on one side, basic solutions on the other side. How would you know? I mean, acidic solutions, normally they start with a hydrogen or a plus charge. So HCl is an acid, HCN is an acid. Acetic acid is an acid, and this is the acetic hydrogen, or the acidic hydrogen is the one that is connected to the oxygen. So this is an acid. Ammonium chloride is an acid because it starts with a positive polyatom. So this is an acid. Hydrogen sulfide is an acid as well, and the rest are bases. So as we mentioned, we are going to arrange those as acids and bases. So we're just going to put the acids in one pile and the bases in the other pile. We are predicting here. So we want to get the pH value, we want to get the Ka value. And based on the pH value, we're just going to go ahead and arrange the acids. So there is since these are acids, there is a pKa table that I posted on eCampus, so you can look at that and you can get the Ka for each of these acids in there, so you can easily find the Ka. For example, the Ka of sulfurous acid, the H2SO3, this is 1.54 times 10 to the negative 2. So you can go ahead and put it over here. So that is 1.54, for example, times 10 to the negative 2. We want to find the pH of the sulfurous acid. So all what you need to do is just go to Google and just type in pH of, because it's a solution, right? So 0.1 molar, and that is sulfurous acid. And then it's going to give you the pH of that solution in there. So if you scroll down, the pH is approximately, this is of 0.1 molar solution at room temperature. The pH is 1.33. So you go ahead and you write that down. For the rest of the acids, like hydrochloric acid, sulfuric acid, these are very strong acids. In the table that I gave you for the acids, you won't find the Ka value. It's very large. So you can go to Google and figure it out. If not, just go ahead and report it as a very large, large Ka. And then go to Google and figure out the pH of a 0.1 molar solution of HCl. Go ahead and put it here. Do the same thing for sulfuric acid. For the ammonium chloride as well, you would need to go to Google in order to figure out the Ka and the pH for 0.1 molar solution. After you do this, you guys, you have to arrange the pHs from the lowest pH to the highest pH, meaning from the strongest acid to the weakest acid. And you're going to put your data over here. So remember, we are arranging from the strongest acid, meaning that the lowest pKa value, right? So we're doing the lowest pKa value, and we are expecting the lowest pKa value is the strongest acid, and this means that we are doing an increasing pH. So we said we're going to start with hydrochloric acid, sulfuric acid. You're going to see from the Ka values that the HCl is a stronger acid than sulfuric acid. And then you're going to do the rest of the acids in there. Now, with respect to your reasoning over here, whenever you have your reasoning, I want you to put your Ka value, and I want you to put your pH value as well for each one of them. And if your Ka value is very large, this means that your acid is very strong and the dissociation is 100% dissociation. If your Ka value is to the power of the negative, meaning it's less than 1, then this is going to be a weak acid. So in your reasoning, you're going to put it's a weak acid. It's a weak acid. It's not 100% dissociated. And then you are going to put the value for the Ka and for the pH. Now, to write down the acid, if there is a number in it, like H2SO4, then you write the letter, and then you do an underscore, and then you do the 2, and then you go ahead and you put your cursor up there, and you write the actual letter. This is an SO, and then an underscore, and then a 4. Okay, that is for the acidic solutions. For the basic solutions. Now, for the basic solutions, you guys, it's a base, right? So we no longer need to look at the acid dissociation. We're going to look at the base dissociation, which is Kb. I did not provide any table for Kb, so you're going to rely 100% on online. Go to Google in order to get the Kb for the different bases. So by definition, this is similar to the acidity though. As the dissociation of the base, as the Kb, this is the dissociation constant of the base, increase, as the basicity is going to increase. And we're expecting Kb to, if it is less than 1, then we are talking about weak bases. If it's more than 1, then we're talking about a strong base in that case. And of course, PKB is going to be the opposite as PKB increase, not decrease. As the PKB increase, the basicity is going to decrease. So the rest of the zero point 0.1 molar solutions, are just going to put them over here, not in order though. So all of these are bases in there. I know that sodium hydroxide is a strong base, so I'm expecting the Kb for the sodium hydroxide to be very, very high. If you search it on Google, it's going to say that the Kb is infinity in there. So just go ahead and report it as infinity. And if you search on Google the pH for the KOH, that is going to be basic. So I'm expecting the pH over here to be, it's going to be around 14, 13 in there for room temperature solution. This is sodium acetate. So search the Kb for the sodium acetate, search its pH value, ammonia, sodium cyanide as well. Search for those, the Kb and the pH. So for potassium nitrate, this is a salt, and this salt is formed whenever strong acid reacts with a strong base. Normally, salts of this kind, they do not hydrolyze in water. So we are expecting that their Kb to be equal to 0. You're going to search on Google. It's going to tell you that the Kb is equal to 0. These are not basic. And the pH is going to be equal. It's going to be close to 7. It's going to be close to neutral in this case. So the KNO3 is going to have a pH which is closer to 7. So KNO3 is going to be between acids and bases. It's a neutral salt. Okay. We're going to do the same thing for sodium hydrogen carbonate. So this is a hydrogen carbonate, and this is sodium phosphate. So you're going to get their Kb, you're going to get the pH. And then after you do this, we're going to go ahead and arrange the pHs from the weakest base to the strongest base. Okay, and we are going to put all our data in here. So once we reach to the highest pH, you're going to see that the highest pH is going to be the sodium hydroxide. The NaOH, this is going to be the strongest base. If it's a strong base, you guys, since the Kb is infinity, it's a strong base, it undergoes 100% dissociation. So in your explanation, you have to state that this is the strongest base based on its Kb value, based on its pH, which is 13, so it undergoes 100% dissociation. All the other bases that are listed, if they have a value to the negative, then these are considered to be weak bases. So again, acids are either strong or weak, bases are either strong or weak. If acids or bases are strong, then they're going to undergo 100% dissociation. That will be reflected by their strong Ka or Kb value, which is greater than 1. And if the acids or bases are weak, then they are going to not dissociate completely. So it's not going to be 100% dissociation, and it will be reflected by their low Ka or Kb value, which is less than 1. So that is going to be for the first part of the experiment, which is going to be the prediction. So you are predicting here for these solutions. Your actual experiment is down there. So we're going to go ahead and open that in a new window. This is going to be the actual experiment. And with this actual experiment, you are going to simply find the pH of the solution. Okay, so we're simply going to find the pH of the solution. The working station is going to open on the live data, and in here, I think you do have the ammonium chloride. So that is the ammonium chloride solution. Now you're going to simply read its pH. Now we're going to continue and pick the sodium bicarbonate bottle and the potassium nitrate bottle. So you go to the stock room. The sodium bicarbonate is a base. So we're going to pick that. The bottle is going to appear on the shelf. And then the potassium nitrate is a salt. We're going to pick that as well. And then after we do this, now we're going to create a solution, a 0.1 molar solution of each in order to measure their pHs. This is going to be in order, you guys. We're gonna go ahead and grab a weighing paper. Actually, we're gonna go ahead and grab the bottle, put it on the spot, open the drawer, grab a beaker, put it next to that bottle, and then zoom in on the balance area, tear the balance, make sure that you put a weighing paper on the balance, make sure that you tear that weighing paper, and now you're gonna open the lid. If you don't open the lid, you cannot do the math. So open the lid of your container, then if you bring your cursor, you're going to see different masses for the spoon over there. So we need the zero point 0.2 grams. Just take the 0.2 grams, put it on the balance, so it's approximately 0.2 grams, and then grab your weighing paper and let it snap above your beaker. Now your beaker has the solid in it. We want to create the solution, right? So we want to dissolve that solid in water. We're going to grab a 25 ml graduated cylinder. Make sure, guys, that it's empty. It says that it's empty first. We're going to put it under the water, and this has to be completely filled. See, right now it says like it's partially filled, so you have to completely fill it. Right now it's completely full, so we're going to go ahead and dump the 25 ml. After we do this, we're going to put the pH meter inside, and we are going to start stirring. So when you start stirring, the solid is going to dissolve. The 0.1 molar solution is going to form. So after the 0.1 solution forms over here, we're going to go ahead and measure the pH. This is sodium bicarbonate. The value of the pH should be very close to the one that you predicted. So go ahead and report it over here. Okay. We're going to stop that by simply disposing it. And we're going to take the solid, zoom in and make sure that you close the bottle. And then we're going to take that bottle, we're done from it. We are going to dispose. We're going to do the same thing for the potassium nitrate. I'm going to go ahead and dispose that. Go ahead and get the value for the pH. For the potassium nitrate, follow the same steps. Sulfuric acid and the ammonia solutions. These are liquids. They are different than the sodium bicarbonate and the potassium nitrate. Those two are solids. So all solids, you follow the same steps as we did for those two. Now for the liquids in there, we're going to prep 0.1 molar solutions of each. So let's start with picking up our bottles for these solutions. We have the ammonia. The ammonia is a base, and we do have the sulfuric acid, the H2SO4, which is the acid. So remember, sulfuric acid, we said this is a very, very strong acid. So its pH has to be very low. Let's do the ammonia first. So we're going to bring that bottle to one of these three spots. We're going to take our beaker, we're going to put it on the bench or on the hot plate. And then it says that here that I need to drag the bottle to fill the 5 ml graduated cylinder. So we're going to go ahead and grab the bottle. This is the 5 ml graduated cylinder, so we're going to fill that. It says full, okay? And then we're going to bring it. We're just going to put it over here. And we have to dilute that with 20 mils of water, and we're going to use the 10 ml cylinder twice to fill it. So where's the 10 ml? This is the 10 ml in there, so we're going to fill it completely. Here you go. When it snaps, then it's completely full. So that is the first 10 ml here, and we're going to do the same thing there. This is partially full, so here you go. Now it's completely full. And we are going to put the pH meter all the way in, and we're going to go to the live data, and here you go. So this is going to be the pH for the ammonia. It's 11.10. Please record it. It is very high. So please record that and do the same thing for the sulfuric acid, but please pay attention to the volume of water that you are going to be using. It's different volumes of water because you're reaching the same concentration. We are going to follow the same steps as we did for the solids and the liquids to prep the rest of the solutions, record the pH, and then submit your answers.